Let's take apart a paper that reverse engineers the tool a lot of us now code with all day. It's called Dive into Claude Code, the design space of today's and future AI agent systems, from the Vila Lab. They read the actual shipping source code and ask a deceptively simple question: what actually makes a coding agent good? The answer, it turns out, is almost none of the model. Here's a number that should bother you a little. Someone measured how much of Claude Code, the real shipping source, is the artificial intelligence part, the code that actually decides what to do next. It's about 1.5%. Everything else, the other 98-odd%, is plumbing, permission checks, context management, tool routing, recovery logic. The part everyone obsesses over, the model, is basically a guest. The house it lives in is the product. So this paper does something unusual. It ignores benchmark scores entirely and reads the harness, line by line, as an architecture. Because if the model is becoming a commodity that everyone has, then the thing wrapped around it is where all the real design decisions are hiding. Let's go find them. Strip everything away and the core of a coding agent is almost embarrassingly small, a while loop. Gather context, take an action, verify the result, and repeat until the task is done. That's the whole engine. The model looks at the conversation and emits a request to use a tool, read this file, run this command. The harness runs it, feeds the result back, and asks the model again. This is the reason and act pattern, and it commits to one action at a time with no backtracking. It trades the completeness of tree search for something more valuable in practice: simplicity and low latency. The clever part isn't the loop itself. It's that this trivial loop is the entire skeleton, and every hard problem in the rest of the paper is a whole subsystem bolted onto one of its three moments: what the model sees, what it can reach, and whether an action is actually allowed to run. The authors put the entire architecture into a single sentence. So why is there anything to study in a while loop? Because moving from autocomplete to autonomous action changes the problem completely. A completion tool suggests text, you accept it or you don't, and the worst case is a bad line you delete. An agent runs shell commands, edits files, calls external services on your machine, sometimes while you're not even watching. That shift creates a whole set of questions that simply don't exist for autocomplete. Where should the reasoning live? What happens when an unrecognized action shows up? Do you allow it, block it, or ask? What's the scarce resource you have to budget? How do you hand off work? And how does a session survive longer than the model's own memory? The paper calls this recurring set of questions the design space. Every coding agent has to answer them. The genuinely interesting part is that different systems answer them in completely different ways. And here's the paper's real thesis. Those answers aren't arbitrary engineering taste. They trace back to human values. The authors pull 5 of them out of Anthropic's own writing and the source code itself. Keep the human ultimately in charge. Protect the human even when they're careless or distracted. Do what they actually meant and let them verify it before trusting it. Amplify what one person can accomplish and adapt to their specific project over time. 5 values. From those, they derive 13 design principles. Things like deny first with human escalation, or treat context as a scarce resource. And each principle lands on a concrete choice in the code. It's a chain, a value, to a principle, to an implementation. That's the lens for the entire system. Every weird-looking decision we're about to see is one of 5 human commitments, made mechanical. Start with the deepest choice of all. Where does the thinking actually happen? Claude Code splits it clean down the middle. The model reasons about what to do. The harness decides whether it's allowed, and then does it. The model never touches your file system, never runs a command directly, never opens a network connection. Its one and only way to affect the world is to emit a structured tool use request, which the harness inspects before executing. Now watch why that's not just tidiness, it's security. Because reasoning and enforcement live on completely separate code paths. A model that gets confused, jailbroken, or hit with a prompt injection still cannot override the permission rules or escape the sandbox. It can ask for anything it wants. The harness is the one holding the keys. This is the architecture behind that 1.5% number. Keep the smart, unpredictable part tiny and caged, and pour all your engineering into the boring, deterministic cage around it. They put an actual number on just how thin that reasoning layer is. If a tool use request is the model's only lever on the world, then the set of tools you give it is the entire design of that world, the agent's hands. Claude Code assembles up to 54 built-in tools before each session. Some are always on, many are switched on by feature flags or by who you are. Then it merges in tools from external servers over a protocol called MCP, plus tools from plugins and skills, and deduplicates the whole thing into one flat pool the model picks from. But every tool you hand the model has a cost. Its name, description, and input schema all eat into the context window. So there's a lovely trick called deferred schemas. When there are too many tools, the model first sees only their names, like a table of contents. The full instruction manual for a tool loads only when the model actually reaches for it. The action surface is designed like a menu you don't read cover to cover. You open the page you need. Now the gate that every single action passes through. When the model wants to run a command, the request doesn't just execute. It hits the permission system, and the answer is one of three words: allow, ask, or deny. And the ordering between them is the whole philosophy. Deny first. A deny rule always wins, even over a more specific allow. A broad block all shell commands cannot be undone by a narrow but allow the test runner. Unknown actions are never silently allowed. They're escalated to you. And it isn't one switch. There are 7 permission modes forming a spectrum, from plan mode, where the model must get its entire plan approved before touching anything, through the normal ask me first mode, up to modes that auto-approve edits or hand judgment to a classifier. You don't pick a trust level once and freeze it. You walk up the spectrum as you learn to trust the thing. Trust is a trajectory, not a fixed setting. Here's that precedence rule, stated exactly in the source. But here's where it gets human and a little uncomfortable. Anthropic looked at how people actually respond to those permission prompts, and users approve about 93% of them. Sit with what that means. If you say yes 9 times out of 10 without really reading, the prompt has stopped being a safety mechanism. It's become a button you mash to get unblocked. Approval fatigue quietly turns your vigilance into pure theater. So the design response is the genuinely interesting part. Not more warnings, fewer decisions. If people are going to rubber stamp prompts, then safety simply cannot depend on people reading them. So you draw boundaries the agent can move around freely inside, a sandbox, an automated classifier, and you reserve an actual human decision for the genuinely unusual case. One analysis found that sandboxing cut the number of prompts by around 80%. The goal was never to ask better questions. It was to ask far fewer of them. This is the finding that reshaped the entire safety posture. Since you can't fully trust the human and you can't fully trust the model, the safety architecture rests on no single wall. It stacks independent layers, and any one of them can stop an action cold. Blanket denied tools are stripped from the model's view before it can even ask for them. Then deny rules evaluate. The active permission mode sets a baseline. An optional machine learning classifier can veto things the rules would have allowed. Approved shell commands can still be forced into a sandbox that limits file system and network access, a completely separate axis. Permission is about authorization, the sandbox is about isolation. And permissions deliberately don't survive a session resume, so stale trust can't leak into a new context. 7 layers, different techniques, so a failure in one doesn't open the door. And notice the elegant bit. When a layer blocks something, that denial isn't a dead end. The reason travels back to the model, which revises its approach and tries a safer path. Enforcement steers the agent instead of just halting it. If watching a supposedly simple while loop grow 7 whole layers of safety machinery is your idea of a good time, do the loop Y thing. Like, subscribe, and send this to the friend who still insists Claude Code is just the model. Right, back to the plumbing that turns out to be the actual product. Here is the resource that quietly governs everything else, the context window. Older models get 200,000 tokens, the newest ones around 1 million, and it is always, eventually, the binding constraint. Every file read, every command output, every prior turn competes for that space, and when it fills up, quality falls off a cliff. So Claude Code manages it like a memory manager, not a garbage bin. 5 compaction layers run in sequence before every model call, gentlest first. Budget reduction trims individual tool outputs that are too big. Snip drops the oldest history segments. Micro-compact does fine-grained, cache-aware compression. Context collapse replaces a stretch of history with a summary, but as a read-time projection, so the full record still exists underneath. And only if all of that still isn't enough does auto-compact fire. A full, model-written summary of the whole conversation. It's lazy degradation. Spend the cheapest, least destructive move first, and escalate only when you're actually forced to. Compaction handles the conversation while it's in flight. But what about the things you want the agent to remember every single time? That's a separate system, and its defining choice is radical transparency. Instead of an opaque database or a vector index you can't inspect, your instructions live in plain markdown files, the Claude.md hierarchy. For levels, from machine-wide policy, down to your personal global file, down to project files checked into the repo, down to a private local one. Files closer to the code you're working on load later and win more of the model's attention. And they're lazy. Deep directory instructions only load when the agent actually reads files there. So your instruction set literally grows as it explores the code base. Now notice what they deliberately did not build. No embeddings, no similarity search. To find relevant memory, the system just has a language model skim the file headers and pick a few. You trade a little retrieval finesse for something priceless in a safety-critical tool. You can open the file and see exactly what the agent was told. Now, how do you let people extend this thing without drowning it? Most frameworks give you one mechanism. Everything you add is a tool. Claude Code deliberately ships 4, and the reason is beautiful once you see it. They're sorted by how much context they cost. At the free end are hooks, little bits of code that fire on lifecycle events to block, rewrite, or annotate actions. They cost 0 context by default. Skills cost a little. Only a short description sits in the prompt, and the full instructions load when the skill is actually invoked. Plugins are the packaging layer, bundling any of the others together for distribution. And MCP servers, which give the model brand new callable tools, cost the most, because every tool's schema has to live in the window. So the 4 aren't redundant. They span a range from zero-cost event handlers all the way to expensive full integrations. A single mechanism could never cover that spread without forcing everyone to pay the maximum price. And each one plugs into a different moment of the loop, what the model sees, what it can reach, and whether an action runs. Sometimes the smartest move is to not do the work yourself. Say fixing one failing test means first understanding an entire authentication module, a big, messy exploration that would flood your context with dead ends. So the agent spawns a subagent. And the key design choice here is isolation. The subagent gets its own fresh context window, its own tool set, does the messy exploration, and returns only a short summary to the parent. All the noise, the 20 files it read, the wrong turns, stays in a separate transcript on disk called a sidechain, and never touches the parent's window. It's delegation as context hygiene. You get the answer without inheriting the mess. Subagents can even run inside a temporary Git work tree, their own private copy of the repo, so they can edit freely without stepping on your main branch. It is not free. Running whole teams of agents can burn something like 7 times the tokens of a normal session, which is exactly why that summary-only return matters so much. It's worth a quick detour on planning, because it's delightfully anticlimactic. Claude Code has a plan mode and a planning tool, and one practitioner described that tool as basically a no-op. It doesn't compute anything. It doesn't call the outside world. So why does it even exist? Because writing the plan down keeps the agent on track. The value isn't external computation at all. It's that laying out the steps focuses the model's own reasoning, and it gives you a clean checkpoint to approve before anything actually runs. And this is the whole philosophy in miniature. The harness doesn't impose a rigid planning graph the way some frameworks do, with typed nodes and edges routing the model's every move. It just hands the model a scratch pad and gets out of the way. Minimal scaffolding, maximal room for the model to think. A production tool spends a shocking amount of its code on things going wrong, and how it chooses to fail is itself a design decision. The principle here is recover silently, and only spend the human's precious attention on what's genuinely unrecoverable. Hit the output token cap in the middle of an answer. Retry with a bigger limit, up to 3 times. Context about to overflow. Reactively compact, just enough to make room. The API rejects the prompt as too long. Try collapsing history and compacting before you give up. A streaming hiccup or the model itself failing. Fall back to a different strategy or to a backup model entirely. Every one of these could have been a hard error thrown in your face. Instead, they're quietly caught and routed around. It's the exact same pattern as a denied permission. A failure becomes a signal the system acts on, not a wall it slams into. The whole agent is built to bend rather than break. Where does all of this lie between turns and across restarts? On disk, as append-only logs. 1 file per session, 1 event per line, written the moment things happen and never rewritten. Append-only is a surprisingly strong choice. You can resume a session, fork it into a new branch to try something different, or rewind it, all just by replaying the log, and every event stays human-readable and auditable. You trade the fancy queries a real database would give you for total transparency and the power to reconstruct anything. But here's the sharp edge, and it is completely deliberate. When you resume a session, your conversation comes back, but your permission grants do not. You have to approve them again. It feels like friction, and that's the point. Each session is treated as its own isolated trust domain. So a decision you made yesterday, in a totally different context, can't silently authorize something dangerous today. Safety wins over convenience. Let's watch one tiny request light up the entire machine at once. You type, "Fix the failing test" in the auth test file. That single sentence fans out through every system we've built. It enters the loop through an interface. Context assembly packs in your Claude Markdown files, the get state, the recent history. The model decides to run the tests. That request hits the permission gate, and because it's a shell command, it asks you first. It reads the failure, decides it needs to understand the auth module, and delegates that exploration to a subagent that comes back with just a summary. It edits the file, reruns the tests, verifies they pass. Every step is recorded to the append-only transcript, and if the context ever got tight along the way, compaction quietly ran in the background. One mundane sentence, and it touched the loop, the tool pool, permissions, context management, delegation, and persistence. That's the whole architecture, working as a single thing. Now the move that makes this an actual study and not a fan letter. The authors take the exact same design questions to 2 other agent systems built from completely different starting points, a multi-channel assistant gateway, and a single process assistant serving many surfaces, plus the wider world of coding agents. And the answers genuinely diverge. Take safety. Claude Code puts the trust boundary between the model and your machine, checking every single action, deny first. Container-isolated agents like Subagent and OpenHands make a totally different bet. Wrap the whole thing in a sandbox and let it run freely inside. Aider makes a third bet entirely. Skip per-action checks and use Git as the safety net, so every change is reversible. Same question, how do I stay safe? In 3 completely different architectures. The gateway system pushes the boundary all the way out to the perimeter, checking who's allowed in rather than what each action does. The lesson isn't that one of them is right. It's that the questions are universal, and the deployment context is what decides the answer. Step back far enough, and a familiar shape emerges. A tiny reasoning core, wrapped in a thick shell of deterministic services for permissions, tools, memory, and recovery. If that sounds like something, it should. It's an operating system. The loop is the kernel. Everything around it is the OS, virtualizing the messy real world into safe, structured calls the model is allowed to make. And this reframes what's actually being built here. As frontier models converge, as they all get roughly, dependably good at coding, the model stops being the differentiator. The harness becomes it. The paper argues, and this is the part one keep chewing on, that investing in boring infrastructure, context management, safety layering, recovery, may buy you more real reliability than bolting yet another clever planner onto an already capable model. The intelligence is a commodity you rent by the token. The operating system you build around it is the thing you actually design. Is that just a nice story, or is it actually measurable? It's measurable. There's benchmarking where you hold the model completely fixed and change only the harness wrapped around it. And a single model score on long horizon task swings by up to 18 points. Same brain, different body, 18 points. That is an enormous effect for something people dismiss as mere plumbing. And on the other side of the ledger, Anthropic's own survey of their engineers found that around 27% of the tasks done with the tool were work that simply wouldn't have been attempted otherwise. Not faster versions of old work, genuinely new work that the harness made feel possible in the first place. So the harness isn't just squeezing a bit more out of the model. It's changing what people even try to do. That is the payoff that justifies pouring 98% of your code into the cage around the model. Now the honest part, because this paper is refreshingly willing to point at its own subject's cracks. Layering safety sounds unbeatable, right up until the layers share a weakness. Security researchers found that a command with more than 50 subcommands falls back to a single generic approval prompt, quietly skipping the per subcommand deny checks, because parsing them all was freezing the interface. Defense in depth assumes the layers fail independently. Here, performance pressure made several of them degrade at exactly the same time. Extensibility carries its own bill. Every hook, plugin, and external server you add is also new attack surface, and some real vulnerabilities lived in the window before the trust dialog even appeared. And all that clever compaction is largely invisible. When your history gets summarized or collapsed, you usually can't see what was dropped. Every one of these is the direct cost of a strength. Layering, extensibility, and compression each buy you something genuine, and each hands you a brand new failure mode as the change. And then the question the paper saves for last, the one that isn't really about architecture at all. All of this amplifies what you can do today. But does it quietly erode what you understand over time? The authors are careful here. They call this a cross-cutting concern, not a design value, precisely because the architecture doesn't actually optimize for it. But the evidence they gather is sobering. Anthropic's own study names a paradox of supervision. Lean on the AI to do the work, and you slowly lose the very skills you'd need to supervise it well. Independent research found that developers working with AI assistants scored measurably lower on tests of actually understanding the resulting code. There's a real tension between amplifying a person this quarter and developing them over years, and almost nothing in the harness is built to protect that second one. It's the rare architecture paper that ends by questioning whether its own subject is missing an entire value. One measurement makes that worry uncomfortably concrete. So, the whole machine, in one breath. A coding agent's power is not the model. It's the harness, 98% of the code. At its heart, a while loop. Gather, act, verify. The model only ever emits a tool request, and the harness owns the keys, which is exactly what keeps a jailbroken model caged. A gate answers every action deny first, across 7 layers, because humans rubber stamp prompts and can't be the only guard. Context is the scarce resource, managed by 5 graduated compaction layers and plain, inspectable memory files. For extension mechanisms, priced by context cost. Subagents that explore in isolation and hand back only a summary. Everything logged append-only, resumable, but never retrusting stale permissions. Trace every one of those choices back, and it's one of 5 human values, made mechanical. The model reasons, the harness decides. That single split is the whole design. The one-line version. A coding agent's intelligence is a commodity, and its architecture is an operating system for that intelligence. A tiny reasoning core inside a thick deterministic shell that decides what it sees, what it can touch, and what it's allowed to do. What sticks with me is that very last question. We now have overwhelming evidence that the harness makes the model more capable. We have almost none that it keeps the human capable. The entire architecture is built to amplify what you can do today, and it's strangely silent about what you'll understand tomorrow. Maybe the next great harness isn't the one that makes the agent more autonomous. Maybe it's the one that keeps you in the loop on purpose. That's my read. Tell me yours. Until next time.